right, so now we're going to talk about resistance. Now, she brought that up at the end of the 4-minute mark that you were watching in the video. I need for you to continue watching that video from the 3:50 mark when she introduces the resistance for the first time all the way to the end. So you get an idea of what this is all about and with her good visuals that she has. So you would please do that if you've not done so already. Alright, so what we're talking about is now electrons, instead of being static like we talked about in the last chapter, they're actually being forced to move. As a push. The voltage pushes these electrons from one side to the other. Now the electrons, like I said, are part of the metallic bonding, where electrons are all over the place as all the atoms of the metals are sharing their electrons with everything else, creating this incredibly tight bond, which is why metals, for the most part, can be very strong, especially when they're in solid form. And she then talked about the relationship between voltage, current, and resistance. Now, a resistor is simply like a speed bump. As the push is going on, remember electrons are moving around randomly. They may not necessarily like to be pushed in a particular direction. There's some resistance to that due to randomness, and because of that, the wires themselves have resistance. Then they get forced into a mechanism that's requiring work to be done within the mechanism that basically kidnaps the electrons for a process before it moves on towards the ground. And so that resistance, which she describes as being measured in ohms, we use the letter omega for ohms. And then the current, which is measured in amps, which we said was joules per coulomb, all together gives us this equation V equals IR. This is called Ohm's law. George Ohm, George who didn't have an E on the end of his name, George Ohm, German scientist, came up with this relationship that we hold even to this day as being an outstanding law. We use this relationship in determining very important aspects of electrical application. So in the example I gave you, we had a home that had 120 volts going through the wiring system. The total resistance of all the appliances was and the wiring came to about 300 ohms, and we want to know what is the current for that. So to figure that out, we just plug in 120 volts for the voltage and 300 for the ohms. We now have a very simple algebra problem. We divide by 300 ohms, and we get 0.400 amps. Now, you probably don't know a whole lot about amperage if you've never dealt with electrical systems, but there are some sections of the house that have higher current than this, but the overall current for the house is 0.400 amps. And when we get into the last parts of current electricity, we talk about something called series circuit, parallel circuit, and combined circuits. And there are aspects of that circuit that will have higher current than other aspects, depending on which kind of setup you have. But this is generally about right. 0.400 amps is still a lot of current. And the last thing you want to do once you get it right is stick a fork in it, because that'll kill you. So here's an example of a wire, what I was talking about here. And it turns out that, like I said, the wires are resistors as well. And so we know that, like refrigerators and stoves and toasters, air conditioners are all huge resistors that the electricity has to go through to get them to work. And then you have really small ones all around the house, clocks and timers and all that stuff. That's minimal. But the wires themselves, if you have a lot of wiring, the length of a wire is a direct relationship with the resistance, meaning the longer the wires, the more resistance you're going to get, which makes sense. To me, the one that's baffling is the next one, and that is the cross-sectional area of the circle. The circle, if you slice a wire perpendicular to the length, you would get a perfect circle as a result. This is called a cross-sectional area. And of course, you find cross-sectional area as pi r squared. So if you have a radius in meters, and everything has to be expressed in meters, because that's the SI unit for length. So if you change your radius to meters and find the cross-sectional area for that, you can calculate the change in resistance. But like I said, this surprised me. But I guess it makes sense if you think about it, because the bigger the wire, the more room there is maybe, or more ability to push the electrons through it. So the resistance actually decreases when you have a thicker wire than you have with a thin wire. The thin wire, there's not much room for those things to go, and so the electrons tend to get in the way. That's my reasoning for it, and I'm going to stick with it. So that's an inverse relationship between resistance and area. So you put the two together, you know, R is proportional to L over A, length over area. Change that to an equation, and we get an equal sign to change that to, and then you have to have a constant. Now, most of the laws we had up to this point, we use like a K of some sort, or a couple times a G or something like that. But here, since we're dealing with resistors, we use the Greek letter for R, which is rho. And it looks like a P, it's kind of a loopy P, but it is the Greek letter for rho, or for R. And that constant, which again is going to have a chart for it. And the chart for these rows, which we call resistivity, is found on page 606. Now, what's also important, I have written here, material. What is the wiring made of? Because every wire acts differently. They don't all act the same at all. So the resistivity is dependent upon length, area, and the material. So when you look up a row chart on page 606, it's going to be different for different types of material. And then you have to calculate the length and the area in how that affects the overall resistance. So let's take a look at an example of that I gave you. We have a 3.5 meter 12 gauge copper wire. Now, wiring is found in gauges. It turns out the smaller the gauge, the thicker the wire. So, a 12 gauge, and you can look, if you ever look up gauges of wiring to find out what the cross sectional area is, they'll give it to you in square inches or square millimeters. And since we're dealing with the SI system, we had square millimeters. We get 3.31 square millimeters. Sometimes you have to actually calculate it yourself using the pi r squared, so be prepared for that. Sometimes, hint, hint. So we need to change the square millimeters to square meters. Now, the way to do that, since you were not taught how to convert square anything to square anything, is simply pretend like it's meters to millimeters, like 1 meter over 10 to the third meters, or 1,000 millimeters rather, and then square the entire fraction. And there is your conversion for it. And in this particular case, this becomes 3.31 times 10 to the negative 6 cubic or square meters. The rho, if you look on page 606 for copper, and you got to look for the copper one, is 1.70 times 10 to the negative 8, and the label for rho is ohms meters, which of course is a nonsense label because it is a constant. Constants don't have labels that make sense. We don't expect them to, and don't ask me what it means. It's just a way to correlate between distance and resistance. Ooh, poetic. Little labelable. So the formula is R equals rho times L over A. We said rho is 1.70 times 10 to the negative 8 ohms meters times the length, 3.5 meters, and the area expressed in square meters, 3.31 times 10 to the negative 6, and we get an answer of 0.0180 ohms.